A 5-minute delay. Let me open the seminar, our regular delay and a regular seminar, Monday seminar, and I would like to welcome Ondřej Dušek, and I would like to ask him to present his project on natural language generation.
Actually is a large part of my PhD thesis, which I am currently finishing up here. And so my supervisor is Filip Jurčíček, so it's basically joint work done with him. And as to introduce what I'm going to be talking about this afternoon. First, I'm going to give a very for spoken dialogue systems and what kind of problems I attempted to solve. And then, like, the three main parts will be 3 experiments in NLG for spoken dialogue systems. First, basically just trying to apply sequence-to-sequence neural network models, which have been successfully applied to machine translation and other areas, also to NLG, and to introduce some improvements to actually make the setup work. Then the second bigger part will be trying to make the NLG system adapt to the context or to the user, make it reply in a way that is appropriate given the user's question, given their wording. And the last main part of my talk is concerned with generating Czech. So how do we adapt this kind of setup to generate Czech successfully, and what kind of problems we can encounter there? So that will be the last part of my talk, basically, and then I'll just conclude. Okay, so first the task or the definition. So my task, NLG in a spoken dialogue system, is basically to convert this kind of meaning representation, which is very shallow and domain specific, and it's called the dialogue act. And I'm supposed to convert it to a natural language sentence that should be human-like and appropriate for the dialogue act and for the dialogue context. There is no content selection, so all the content that is included in the dialogue act should also be included in the sentence, and nothing more. So this is the task here. Other NLG systems usually do some content selection, but that's not the case in spoken dialogue systems. In a typical, like, traditional spoken dialogue system pipeline, this is where NLG is located. So the user gives a request, which is recognized. Then there's some semantic parsing going on. Then the dialogue manager decides, based on the content of the user request, what to do next, how to reply, and it decides on the contents of the reply. So basically the output from the dialogue manager is this kind of meaning representation, and the natural language generation module is then supposed to convert it to a sentence that is then synthesized and read back to the user. So this is the area that I'm concerned with in my talk. And now to the problems. The first problem that I was trying to solve is generating from data without any fine-grained semantic alignment. So typically for most previous spoken natural language generation systems, there had to be either manually provided alignment between the elements of the meaning representation and the corresponding words or phrases in the text, or there had to be an alignment pre-processing step. So that means that the whole setup is more complicated. There might be some errors on the way, and what I'm trying to do is to learn the alignment jointly. So this is the kind of training data that I'm working on. There is no alignments in here. It's just pairs of meaning representations and corresponding sentences. That means that we don't have any error accumulation in a pipeline, and we don't need any manual annotation for the alignments, and also the alignment does not need to be hard. There are also cases where you basically cannot tell whether the word is aligned to a specific element of the meaning representation or not. If you look at, for example, if you look at this sentence, there is the restaurant is conveniently located near X, right in the city center. So if you look at the words conveniently and right, you might say that they are somewhat aligned to the area, but not not in a hard way, or you're not completely sure. And I would like to leave this decision up to the system and do not concern myself with it separately. So this is the first problem, but there is a caveat in in this, because it is still limited even in my setup, because I use delexicalization. That is a limitation to this completely unaligned setup, or you can look at it as a way to address data sparsity. The thing is, basically, if you look at these data elements, these are from two different domains. This is bus information, this is restaurant information, but if you look at them, a lot of stuff is actually, many of those values are actually never or just very rarely seen in training. For example, you would have to enumerate all time values. So it's quite natural to, and you can see that they appear on the output exactly the same as on the input. So it's quite natural to just say that we replace them with placeholders during the generation time, and instead of a concrete departure time, we just have this placeholder, and after the generation is finished, they are basically added back, or the concrete values are replaced in the generation outputs. This is still different from full semantic alignments, because this can be obtained by simple string replacements. This is only for the values that appear verbatim on the output. If you look at the second sentence, there is this value kids allowed equals no, and yes, there is the word no, but if the sentence, if the meaning representation contained the word yes here, the word yes wouldn't appear anywhere in the output. And you could also say that children are not allowed or something like that. So it doesn't have to appear always in the output. So this is not applicable to values of the meaning representation like this. But usually, if it's just binary, there is enough of data for both values to allow for successful training. So this is just a side note on the unaligned data, and I will also use it later on in the presentation. Also, this can be applied to some or all slots. You can decide, for example, in my first experiment, it's only applied to so-called non-enumerable slots, so restaurant names, phone numbers, and postcodes are replaced. But for example, the type of cuisine or price range is left in the output, and it's not affected during the generation. So this was the first problem that I was trying to solve, and the second one is comparing different NLG architectures. Because traditionally, the NLG pipeline is divided into two main steps. The first one being sentence planning, where basically the overall sentence structure is decided and a sentence plan is created. This is actually a very simplified tectogrammatical tree used as a sentence plan. And in the second step, this sentence plan is then converted to a surface text with all the inflection and word ordering and all the surface phenomena. However, some NLG systems actually joined these two into a single step. So this is how it looks like. There is no intermediate step using the sentence plan trees or any other structure. And what I would, and actually both of those have their advantages. The two-step setup basically simplifies the generation by abstracting away from problems of surface grammar like morphological, morphological agreement. And the joint setup avoids accumulation of errors over a long pipeline. So they both have their merits, and I would actually like to compare them. And I can do that in the same architecture, basically. So this is the second problem that I've been trying to address. The third problem is adapting to the user. In a normal human-human conversation, speakers are usually influenced by what has been said previously, so they tend to adapt to each other. They reuse words and syntax, even prosody from the other people. And if you look at this example, if the user asks, how about the next ride in a public transport information context, then if you have a human operator, he is more likely to say, I'm sorry, the next ride was not found, instead of saying, I did not find a later option, which is basically completely changes the wording. So I would like the NLG system to be able to do just that and to adapt to the wording of the user and provide, hopefully, contextually appropriate answers. Also, another thing is this is actually a natural source of variation in dialogues. Whereas if you look at the current NLG systems, they are usually very repetitive. And they basically have no way of addressing the previous context because they only take the input meaning representation into account. And any possible output variance must be somehow fabricated, for example, by sampling from a few different outputs. So what I would like to do is have natural variance and have context-appropriate answers. This actually has not been done in NLG so far, only in rule-based systems and only in a very limited way. And my system should be able to do this, and you will see it in the experiments. And the last problem is multilingual NLG. Actually, most NLG systems have previously been only applied, or most statistical NLG systems have been applied only to English, where there is little morphology. The vocabulary size is relatively small compared to other languages. There is almost no or very little morphological agreement, so you don't have to care about that. And most importantly, there is no need to inflect proper names. So if you're using delexicalized generation, as I am doing, the lexicalization process is just copying the names or the values from the dialogue act and inserting them into the delexicalized outputs. Actually, if you have rich morphology as we have in Czech, none of this works. And they are a little bit outdated, but I think they're still valid. These are examples from Facebook and Doodle. If you have the sentence, the person likes this on Facebook in Czech, it's actually translated like that. This is liked by user and the name. The word user is inserted here to avoid inflecting the name. And also, the user is always masculine, and actually the name may be feminine. So there's even one more source of disfluency. Same for doodle, where the vocative case is not used because the system has no way of inflecting the name, and instead it uses nominative, which is also not very fluent. So Czech is actually a good language to try these things and to try and address inflection, which is why I have chosen it. And I needed to add some extensions to my generator to address this and to basically to inflect proper names, and also to address the large vocabulary by generating lemmas and morphological tags instead of word forms. So these are the problems. This is just a short summary. Basically, I've created a sequence-to-sequence based natural language system that is trainable from unaligned data, and it has multiple modes of operation. It is capable of generating sentences token by token in one step, or to generate deep syntax trees, simplified T-trees, and which are then post-processed by a surface realizer. It is able to adapt to previous user utterances, and it works for English and Czech. And in Czech, it has a third mode where it generates lemmas and morphological tags instead of word forms. And also, it includes proper name inflection. So this is just a summary of what's to follow. And the first part is the basic sequence-to-sequence generation setup, how to make it work on a very small English data set. This is just a brief introduction of the sequence-to-sequence architecture. It's the standard sequence-to-sequence model with attention that has been already used for machine translation and other tasks. Basically, it starts with a recurrent neural network that encodes the input, in this case, a sequence version of the dialogue act, into hidden states, basically vectors of floating point numbers. Then, the second step, the decoder generates the output tokens one by one from the start, starting from the last hidden state, and using the previous hidden state and the previously generated word. If you look at this word, it goes into the next step as the input. So this is the sequence-to-sequence model, and now the attention model is basically a way of weighing the input hidden states and guiding the decoder basically in telling the decoder where to look at and which of the parts of the input is more important. Basically, a means of aligning the pieces of the input to the output. But this is basically a very standard architecture nowadays, and you can do basic greedy generation, selecting the most probable output at each point. You can also add beam search, which is what I have done, and then you always keep an n-best list of outputs. And what I have added in order to make this actually work is a re-ranker for the outputs, and that I'm going to introduce in a bit more detail. It is very simple, but the problem is that this basic setup may not cover the input perfectly, so there might be some missing information on the output, or even some superfluous information that the generator basically hallucinates out of the blue. And I would like to penalize such cases and only output cases that are perfect. So the obvious solution is check whether the output on the n-best list conforms to the input, and then penalize if it doesn't. So I basically just take the output of the generator, run it through a recurrent neural network, and then from the final hidden state there is a classifier that provides a number, a 1 or 0, for every possible piece of information that might be included. It's a kind of one-hot representation of the meaning. And then I have the input dialog act, for which I can provide also the same representation, and I can basically then just check what ones and zeros do not match, and this is the penalty that is then used to basically demold some of the n-best list outputs to the bottom so that they are not produced as the outputs. So this is basically how the re-ranker works. And now to the whole system workflow. This is what I have been talking so far. So you have the meaning representation, and then you have the generator, and you either generate sentences word by word, token by token, or you generate sentence plans which are then realized. Yeah. And in the second mode, what is generated is this, but it looks like this. So these trees are converted to a bracketed notation, and this is only the generated output. So you can see the lemmas, you can see the formemes, and the bracketing basically decides the structure. So this is how it looks like in the more complex two-step mode. And the other mode is just sentences, as I've said. And now to some experiments. I've been using the Bagel dataset, which has been created previously for NLG, and it's very small actually. It's just 400 sentences in restaurant information. It's much less data than what has been tried for any previous sequence-to-sequence generation model. It's partially delexicalized, so restaurant names, phone numbers, and such are replaced by placeholders. There is actually manual alignment provided for the original systems that has been used with this data set, but I'm not using it in my experiments because I'm trying to do without it. Yeah. And yeah, we use BLUE and NIST in a cross-validation scenario. And I also looked at the data manually and checked for errors to see whether the outputs actually conform to what they should. These are previous experiments on the data set. This is the author of the data set who has been using the alignment, so he has got a very high BLUE score and no semantic errors, which basically follows from the fact that he used those alignments. This is my setup from 2 years ago, and you can see it. The BLUE score is almost matching the original authors, even though the task is much harder, but there are lots of errors on the outputs. And this is how I have done with my current setup. The first part of the table is with using the deep syntax trees and the two-step setup, and the second part is just direct generation into strings. If you look at the results, you can see that for greedy generation, it doesn't really work that well. It's worse than my previous experiments. But once you add the beam search and the re-ranker, it actually gets better results for both setups. It gets less semantic errors. And if you compare the two-step setup using the deep syntactic trees and the joint setup, you can see that the joint setup actually does slightly better in terms of the automated metrics, in terms of blue scored. And it's about the same in terms of number of errors on the output. I can show you some examples of how the output looks like. This is the input dialog act. There is the reference provided by humans. You can see that the name of the restaurant is delexicalized, and the reference says X is a French restaurant on the riverside. And if you look at on the regeneration, you can see that there's actually lots of errors. This is not very fluent, and there is a wrong cuisine indication. If you apply beam search, it's still not perfect. There's still some errors, but once you add the re-ranker, the errors go away basically. I have some more examples, but maybe later in the discussion I can show them. So this was my first experiment with the sequence-to-sequence models, and now I'm going to talk for a while about my extensions to adapt to the user. So the goal was basically to condition the generation on the preceding dialog context, but the problem is there are too many possible contexts, even in a very limited domain such as restaurant information or public transport information. So the solution that we came up with is to condition the generation just on the preceding user utterance, because that's likely to have the strongest impact on how you reply. It's probably not that meaningful to condition on something that was 4 or 5 turns ago, because that shouldn't influence the talk as much as the immediately preceding sentence. And the main problem was that we actually needed data that are context aware, where the context is taken into account, and there was no such data set for NLG, and that's why we collected a new set. And in addition to the input dialog act and the corresponding sentence, which is what usually an NLG dataset contains, we added the preceding user utterance. So here you have the user question, then a reply from the system in the form of a dialog act and the corresponding sentence. And also the sentence is context aware. So if the user said, "I'm headed to Rector Street," the system might, for example, choose heading to Rector Street from Fulton Street, basically begin the sentence with what the user just asked about, and then introduce the new information. So this is actually an example from the dataset, but there are more of those. So the way to get these utterances at basically lowest possible cost and shortest possible time that we came up with was to first get some natural user utterances in a call to a real spoken dialogue system. So we have real people on crowdsourcing platforms calling the Alex spoken dialogue system that Filip Jurčíček has been developing here. And we gave them some assignments. Basically ask about a public transport connection or schedule from one stop to another, then modify the search in a few ways. And the descriptions were generated actually in a way that there are many possible synonyms, so that the users are somehow not primed by exactly the same word every time. So, for example, all of these basically say more or less the same, but the first one says you want a connection, your departure is this, and you want to go there. The other says you are searching for transit options leaving with the destination. So it's exactly the same information, but said in a completely different way. And the users actually were not aware that the wording mattered. So this way we got some user utterances, which we then had manually transcribed and reparsed so that we knew the semantic content exactly. So we are using manual transcription for parsing, so that there's no added noise from the speech recognition. Then we generated, using a very simple rule-based policy, we generated responses to those user requests. So these are actually artificial. And then for those responses, for the response dialogue acts, we collected natural language paraphrases in another crowdsourcing task where the interface was designed to support entrainment. So the users were given the information and then the task, and then the last thing that they've seen is the exact request. So they had the context exactly at hand, and the description that they were given to the slots was really minimal, basically just prepositions. The word stop was not included. If there was a time, it was just the time and nothing else about it. The instructions were very short, basically just respond in a natural and fitting English sentence, but there were many checks if the response actually contains all the information that is supposed to be there. We also checked some spelling, and then finally I had to check all of these manually and resubmit the task if some of the replies were not correct or contained some irrelevant information or something like that. So there was about 20% overhead. So now that we have the data set, we can try and improve our sequence-to-sequence generator to actually take the context into account. And we've come up with two very basic and very direct extensions to this setup. This is exactly what you have seen in the previous part. The encoder and the decoder and the attention model. And the first extension is just to put the whole preceding user utterance into the encoder along with the information to be generated. So here we actually mix the user utterance and the dialogue act in the single decoder, and then just try and see what comes out. And another option was to use two encoders. Here you have one encoder, the original one for the dialogue act, and another encoder for the user utterance. The encoder hidden states are concatenated, so the decoder basically has all the information from both sources. So this is another option, and we just wanted to compare those and see whether one of them works better than the other. And in addition to that, we added one very simple technique. As I've said, we're working with n-best lists, so we can re-rank them and play with them after the generation has taken place. And this is a very simple method to basically look at the outputs on the n-best list, look at the preceding user utterance, and promote those outputs that have some word or phrase overlap with the with the preceding user utterance. So basically, if the user asks, is there a later time, and we can look in the n-best list and promote those outputs that have the word later or is or time, whatever we can find on the n-best list. And we basically just increase the probability of these sentences slightly so that some of them might make it to the top of the list. And now for the experiments, I've been working with the data set that we have collected and basically using the same methods, looking at BlueScore and NIST. Actually, in this case, we had a way of measuring the semantic errors automatically, and there were almost none, so I'm not even including it here. But if we compare the setups in terms of the automatic metrics, we can see that with the baseline we get a pretty nice score. If we just use the re-ranker without any changes to the sequence-to-sequence model, we get a nice improvement of about 2 blue points. And if we use any of the improvements by themselves, or the extensions to the architecture, we actually get worse scores. But if we combine those extensions to the architecture with the re-ranker, we get better scores than just using the re-ranker alone. So it's basically half a blue point more than what we could have got only by using the re-ranker. And if we compare the two options, we can see that they're basically the same, or that there's not much difference. So I've then used just this single encoder architecture. And this was actually surprising because this did not happen on the development data, but it did on the test data. And I assume that basically if you add this context information into the sequence-to-sequence model, you increase the amount of noise, and that's why probably a lot of the very appropriate responses make it somewhere onto the n-best list, but not to the top. And then the n-gram match re-ranker is able to promote them and provide even better outputs. I've also done a very simple crowdsource human evaluation. It was just pairwise ranking. The people got the baseline. Got the baseline output where context has not been used, and the output of the best system where the context has been used. And they were just supposed to compare it. Basically says A is better or B is better. And actually the context-aware setup was slightly more preferable. So this is actually statistically significant, but the difference is very small. And that's probably because the difference in those outputs was also very small. So sometimes the users actually preferred, for example, the longer output, even though the other one was actually more context-bound. So it's quite hard to evaluate, but I was still very happy that the context-aware setup was preferred, or more preferable in a majority of cases. So this has been, now just some examples of the output so you can make an opinion for yourself. And here you can see the preceding user utterance. This is the input dialog act, and these are the different options for generation. So in the baseline, you can see that there is basically no word overlap or any kind of correspondence in the outputs. But once you start using the context-aware setups, you can always or almost always find some match or some overlap. And as a confirmation of what the user has just said, these probably feel more natural. Even here, if the user says, I need to find a bus connection, then I did not find a bus route, or I cannot find a bus connection, probably sound more natural than no bus found, sorry. Maybe even disregarding the context. Okay, so this, oh, I have more examples. Sorry, kind of forgot about this. Yeah, here, this is a more problematic case because if the system is just confirming what it just has heard, there is much more space to introduce some alignment between the user and the system. Whereas when it informs about a new information, there is not so much space, but still some of the outputs actually did contain some overlap. So if the user says, I rather take the bus, then it's more natural to say you can take this bus and then provide the answer, instead of just saying, starting with the time and saying a basically generic response. So this is for the context-aware setup, and now to generating Czech. The first problem, same as last time for Czech, has been that there are basically no NLG datasets available except for English. There's one dataset for Korean, but definitely non-NLG datasets are available for, or have been available for Czech so far. So we wanted to create a Czech NLG dataset, but using crowdsourcing, as we did last time, was not exactly an option, because you basically cannot find any Czech speakers on the crowdsourcing platforms. And we also didn't want to have just one or two persons write the whole dataset, because that way it probably wouldn't be very very interesting. There wouldn't be a lot of variance. So what we decided to do is to translate an existing English set that is on restaurant information. It's a different set than what I've been using in my first experiments. It's much bigger, actually. And this way, it's actually easy to hire some translators, and we kind of counted on being able to preserve the variance that was contained in the original set. So that's why we didn't start from scratch. But we also wanted to make it as fast and as cheap as possible. So we actually realized that a lot of the sentences in the original data set are actually identical if you don't look at the restaurant names and other values. So the first step we have done is to delexicalize it, basically replace it with placeholders. Now you can see that both the sentences are actually exactly the same. And this way, by removing the duplicates, we get about half the size of the original set, and this is what went into translation. And before translating it, we actually localized it in a way by replacing the names of restaurants and areas by names of restaurants in Prague and areas in Prague, but actually they didn't have to go well together. So, for example, Ferdinanda actually is not located in Hradčany, but so the combinations were largely random. But that didn't basically did no harm to our experiment, because my main the main reason for doing this was basically to have values that have to be inflected in the output. So in a Czech sentence, you will have to inflect these kind of restaurant names and these kind of area names, whereas if we kept the original English ones, they probably wouldn't have been inflected by the translators. So that's why we changed all the values to Czech ones. Then we had the translators translate those. They actually did not see the dialogue acts. They only saw the English sentences, and in some cases they actually produced errors. Probably not this kind, but they did so. And then I've ran some automatic checks and actually made sure that the sentences contain all the values that they should. And then I've basically expanded the size of the data set to the original by replacing the values with different ones, so exactly as it was in the original data set. But the problem is now that actually more errors may be introduced by this, because you wouldn't say in Czech Café Savoy is levná, because Café Savoy is a neutral gender and levná is a feminine gender adjective, so those errors then have to be checked manually. So I basically had to read the whole data set and correct the errors like this. So this way we came up with a data set that is more or less identical to the original English one, contains exactly the same amount of instances and more or less the same distribution of dialogue acts. It just contains Czech values which need to be inflected, and that's what I wanted to look into in my experiments. And in order to address the problems that come out of generating Czech, I've introduced a few generator extensions. The first one, or like the most important one, is adding a third generator mode. So in addition to generating token by token the word forms and to generating deep syntax trees and having them processed by a surface realizer, I now have a third mode, which is a compromise between those two. And I basically let the neural network decide everything in the structure except for the morphological inflection. So it doesn't generate words, it doesn't generate trees, it generates lemmas and morphological tags. So basically this is the output of the third generator mode. It's just, it's not like this in a column format, it's just a simple sequence where it reads like this, line by line. So you basically interleave lemmas and morphological tags. And then I'm using the Morphodata morphological inflection dictionary with a special list for inflecting some restaurant names that are not included. And this is used to post-process the output of the sequence-to-sequence model and to create the concrete sentence. So this is how the third generator mode works, and this was done basically mainly to address the much larger vocabulary in Czech, the much bigger number of surface word forms. And to address the need to inflect the slot values even in a delexicalized generation scenario, I've added basically two baselines and two different ways of inflecting them, the values based on language models. If you look at this example, here you have the dialogue act basically confirming whether you want to find a restaurant for a brunch. And this is the delexicalized output. And here this value has to be replaced by the word branch or something else in the proper form, because in some cases you actually don't want to put just the noun here. You might even have verbs. So there are many options. It's not one-to-one. So actually, for this case, you have over 70 possible options to put in here. You can use brunch. You can use pozdní snídaně, like a late breakfast. You can use a verb like have brunch, and you have to select the correct form to put in here. There are two baselines, basically just taking one at random and shoving it in here. Another one is looking at the training data and selecting the most frequent form. It's actually a very strong baseline. And then I have two language model-based approaches, a simple n-gram language model and a recurrent neural network-based language model. Basically, going from left and looking at the preceding words, and then they both are able to provide a probability distribution over the next token. So I can have a probability distribution over these and select the most probable form. So this is the way of inflecting proper names. And then there is one other problem that I actually found in the data, and that is that the different values actually have different morphological behavior, not only by themselves. Not only they have to be inflected, but they also influence some parts of the rest of the sentence. And for example, they either require some gender, or they might require a specific preposition, because even though this means in Karlín and in Smíchov, and there is just one preposition in English, in Czech saying na Karlíně or ve Smíchově doesn't sound very natural. So I wanted actually to somehow control for that. And if you look at the data, you can see that in a fully delexicalized scenario, you basically have no way of controlling for that, because the values are not there. So I thought, let's put them back. Let's put them back into the sentence, or into the dialogue act, and keep the sentences delexicalized. This way, I don't have to learn to generate unseen outputs, but I can see the exact values on the input. So basically the generator can then somehow, or should be able to adapt to the concrete values and introduce a corresponding sentence structure. This is actually kind of a proof of concept experiment, or a bit of cheating, because here I am basically exploiting the fact that I just have about 15 different restaurants in the set and about 15 neighborhoods. If there were much more, I wouldn't be able to just put them into the dialogue act. I would probably just have to use some morphological properties or use some fancy neural network way of dealing with that. So this is kind of a proof of concept experiment. What happens if we know the exact values, and what happens if we know how each of the values behave. So this was the last kind of extension that I've added to the generator. So let's look at the experiments. Actually, on the first side, you can see that the outputs that are generated are understandable Czech. There are some fluency errors, in some cases quite a lot of them, but semantic errors are very rare. So basically the output actually really corresponds to the input in most cases. Now for the automatic scores, you can see they're much lower than the English ones, but this is because we're dealing with Czech here. There's still most of the sentences are still actually quite fluent. And if we compare the different setups, I know that there's too many of them. We can see that basically the lemma tag generation and using the lexical information in the dialogue acts, using the values, seems to help. So we get the best blue score. And we can see that actually the direct generation to strings actually works also quite well, but not while combined with using the values in the dialogue acts. We can also see that using the deep syntax trees and this more complicated two-step setup doesn't seem to help very much. Sentences are still quite fluent, but they contain a little bit more errors, and the blue score also doesn't capture that that's so well. So they actually achieve only lower scores. This is basically what I've said. And the other thing is, if we compare the different approaches to the lexicalization, we can see that using just the random setup is much worse than any of the others. And the most frequent baseline is very strong, and sometimes the n-gram model is not even able to beat it. But actually the neural network based language model works best and is always able to beat the baseline. So this is the automatic scores, and as some of you might know, I've also performed a human evaluation, and I would like to thank all of you who participated. You really helped me a lot, and I know that I promised some goodies, and they're coming soon. Trust me. So yeah, I'm really sorry that I wasn't able to kind of process all of this faster. Now, as some of you are aware, I basically use the same method that is used every year to evaluate machine translation. So it's just relative comparisons, basically selecting the most preferred setup out of 5 or up to 5, and then ordering the rest according to personal preference. True skill ratings are used to actually evaluate those with bootstrap clustering to establish statistical significance, and this is the result that I've got. And actually here these are the blue score values for comparison. So as you might notice, they actually doesn't correspond that well to the human evaluation. And so what I found is that actually not using the lexical values in the dialogue act is kind of more preferable, has been more preferred. Using the joint setup with direct word-based generation is more preferable than using my new lemma tag extension, but the recurrent neural network language model for lexicalization is also the best option here. So this is a very different result from what I got from the automatic scores, and that's why I wanted to actually look at that, and I've taken a sample of the best or the most preferred setup and the best blue score setup, and I try to compare both of them, and basically I didn't look at any synonyms or anything. I just compared different kind of specific errors that the generator is likely to make. So I've looked at errors in the way the values are lexicalized. So here, if you look at this sentence, restaurant Švejk is a cheap venue close to Stromovka. The word cheap is feminine, but it should be should be masculine, because the word venue is actually masculine in Czech. So this kind of wrong lexicalization was one error type. Another error type was general fluency errors. In this sentence, this word basically should not be there. There is, you can call to restaurant u Končelu at the number this and that, and this is the word price, which is not connected at all to the content of the sentence. So this is also a kind of error that I encountered. Then there are some errors regarding the sentence structure. This is an error that actually I haven't thought of, and it did occur in the outputs for all the setups, disregarding any extensions. And that concerns the behavior of Czech numerals. Here, there are 3 restaurants in the offer which have all kinds of foods, and if you use the word 3, then the sentence should have been jsou 3 restaurace, not yet 3 restaurací. That is very unnatural, and this construction is actually used for numerals higher than 5, basically. So the system didn't look at the concrete value and wasn't able to adapt to this. So I would have to probably introduce some features to adjust for this. Another type of error, but very rare, are semantic errors. And in this case, the system kind of messed up to the 2 types of information that it was supposed to convey. So it was supposed to say that there are 2 restaurants in Hradčany that are not suitable for children, but it says that there are 2 restaurants not suitable for Hradčany that are not suitable for children. So it doesn't really make much sense, but you can understand why the system was able to produce such output. And like the last type of errors is just punctuation. In lots of cases, the system basically didn't produce the final punctuation, but that's not a very grave error, I must say, but I did count it. And if I compare the 2 setups, the best blue setup got 22 errors, and the most preferred setup in the human ratings got 24 errors on a sample of 100 sentences. So it's actually pretty good. And there were like 1 and 2 semantic errors, so it was very low. But the most preferred setup basically just didn't bother with the final punctuation, and if you discount the punctuation, it seems to be slightly better. So I have to agree with all of you who evaluated the setups and say that the setup that you preferred is actually better than what Blue Score has rated. So this was basically the final experiment, and now just to sum up, I've created an NLG system that is able to generate from unaligned data, and it's better than my previous work on the beta data set, which is very small, so it's able to produce valid output even with very limited amounts of training data. It allows to compare a 2-step setup with a separate surface realization and sentence planning using the tree generation and a joint setup that generates words directly. It's the first system that is fully trainable and capable of training or adapting to the preceding context, to the preceding user utterance. and it's able to work on Czech more or less successfully, including the inflection of proper names, even though there is still a lot of room for improvement. Basically the thing that I would like to improve as the first one is to come up with a way to remove this delexicalization business, because it's complicating the setup very much, mostly, not so much for English, but a lot for Czech. And another thing is I would actually like to test this in an end-to-end spoken dialogue system, which is what I haven't done yet, which was kind of expected, but in the end all of my experiments are basically just standalone. So thanks for your attention, and now I welcome any comments or questions.
So now, thank you very much for your presentation, and now the floor is open for questions and discussion. Yeah.
I have two questions, by the way. Thanks for the great talk. The first question is about the sequence-to-sequence models. Mm-hmm. You quite simplify the structure of the input. Unlike the output, when you generate the bracket notation, you just remove everything and make the slot names and the dialog act names tokens of the same type as the delexicalized value. So my question is, have you tried the bracketing notation as in case of the output, or?
You mean in this case,
yeah,
like using some bracketing notation?
Mm-hmm.
Actually, I haven't, but I think if you look at the, come up with a dialog act somewhere. Here, if you look at the structure here, it's shallow. There basically no nesting is allowed. Mm-hmm. There is just the main dialog act type, which is repeated several times on the input, that I must admit, and then there is just a list of slot and values. So there's basically no other type of structure. It's very shallow. So I don't think that it would help. I think it would actually introduce more noise, but I'm not sure. Maybe yeah, I can try it. I don't think that this would mean a very difficult change to my system. So it's probably quite easy to try it out, but I wouldn't expect much difference in the performance.
Another related question is: did you somehow sorted the slot names, or are they in the random?
I did actually. They are sorted alphabetically according to the slot name.
Mm-hmm.
But even if I didn't, there was not much difference. Mm-hmm. It was like very minor. Like I think it was like half a blue point or something, even less maybe.
Cool.
I think it would depend more on the random initialization than on the actual sorting or not sorting of the inputs.
Okay, thank you. And my second question is about the evaluation. Did you try to measure the correlation of the blue score with the human rating?
Actually, I haven't computed the overall correlation. That's actually an interesting thing to do, and I probably should include that in the text of my thesis because it's actually not that hard to compute, right? So yeah, thanks. That's a really good point.
Okay. Thank you.
It's just on the way, so I'm sorry, but you said, is there a demo of that? Like, is it possible to test it or see it?
Like an online demo? Unfortunately not.
Anything good?
You can download it and install it. It's a bit of a hassle, and it works. Other people have already installed it, but I haven't created any online demo. I think it's quite possible, but given my workload, I wasn't really. It wasn't like on top of my priorities.
Sure. But it'd be great, especially for the students. And
that's true.
Anyway.
That's true. That's a good point.
Thanks. So I have several things, but maybe it's just the main thing. So so one thing that you observed is that the people don't care for punctuation, whereas Bleu cares for punctuation.
Yeah.
So like a simple question is, have you tried computing Bleu with ignoring punctuation? Like removing it from reference in the text or something?
I haven't.
Like it seems like a way around.
Another good point to actually try that, and because that's also very easy to do.
And then kind of more important thing. So it seems that you use neural networks for the generation, but then you still rely a lot on the re-rankers, which are non-neural, if I understand it well.
Actually, they are. One of them is neural, one of them is non-neural.
Okay, so okay, yeah. And still, so have you thought of trying to integrate the re-rankers like into the neural network? So probably they have information available that is not available to the neural network, so it cannot learn the things that the re-ranker is learning. So the engram matches, it looks like you could just use another type of attention that would just directly look at the identities of the words on the input, so then it would have the knowledge of whether this exact word was there or not. I
haven't tried that, but it's really interesting, and I really like to look into that, because that the main problem of this context re-ranker is that it's kind of artificial, or
that's what I mean. So you introduce something more of artificial, whereas if you would train it as part of the neural network, so it could just use it as a feature, not as a hard constraint.
Right.
And
definitely a thing to try.
And with this one, I thought of some papers I saw on MT on explicitly learning a coverage vector or something like that, which looks very much like what you're trying to do here ex post.
Yeah.
So if you would just force the network to learn a coverage vector by itself, whether these slots are covered or not, it seems like it could do the same thing as part of the neural network. But of course, that's kind of hard to do practically. But but
I can at least try, because this is also it makes the architecture more complicated. So having just a single network would be much more elegant, and I would definitely like to have that.
Okay, thanks.
Thanks for great talk. And I know what are the advantages of this solution with neural network. It's end-to-end and it's trainable. But I know also that in your previous work you had also some rule-based generation. Maybe that was the one cited there, or not really?
Even though it was not exactly rule-based. The only thing rule-based there and here is the surface realizer.
Yes, and the surface realizer here is fully rule-based or not?
Except for the morphological inflection step, it's fully rule-based. It's Streak's realizer, so I assume that you know it very well.
Yes, and that's my question. Well, I think that the errors we saw with the agreement morphological and numerals 5 and higher and so on, these are kind of reoccurring here for each 10 years. We see them again on the slides, and
it's true that the realizer should be able to basically to handle them. But the problem is that you have the delexicalization there, and the realizer is still working with the placeholders only.
Okay,
so that's why it cannot see what kind of numeral is processed, and that's why it just chooses the most frequent form.
Okay, thank you.
So, haven't I missed anyone who would like to ask something? Well, if not, then I would like to thank you again for your presentation and wish you good luck
Thank you.
in the further steps which you indicated. So thank you again, and we'll meet
Thank all of
next
you.
Monday. Thank you.